So, okay, so this is another slide, routing lookup process. What happens when we have a router? And let's say we have multiple routers. They are all connected with the same destination. Let's say X. And here we have this the source. Okay, so it means this router is learning multiple these destination from different routers. Okay, so but what happens, this source want to reach this destination. So when this packet will hit this router, what is going to happen? So this is I'm going to explain. When this source is opting for this destination and when will hit this router, what process it need to go through. So the first thing, as it is mentioned, inbound packets need to go through the following process. Find the longest match to the destination. This is our first step. After it found the longer match, either it could go through recursion process or it will go to the outgoing interface. And I'm sure you have some confusion here, so that's why I have a next slide ready for that for you, where I'm gonna explain this thing. Okay, so please pay your attention. This is uh, first of all very informative, and it is gonna haunt you till your CCNP or even the CCI. If you understand it here, no problem. If you don't get it, just go through slide again. And what I'm saying, just go through again. You go to the Google and read it about a lot in detail if you have any confusion here. So here we have a data, which is 172.16.1.1, and it will hit this router 1. Okay, then we have multiple destinations, S0, S1, and S2. As it is mentioned, these are the interfaces. So when the data hit this router, either it could go R2, either it go to R3, or either it go to R4. So how on earth this router is gonna know on which interface I need to go or exit? So this is the process of the longest match. What is happening here? This is routing information inside the router. Router has multiple destinations here, 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 which is learning from these routers. So when this source is coming and it is opting for this specifically this address, it wants to reach to this destination. This is the destination IP. And when it will hit the router, router will go through the process which is known as routing lookup, and under routing lookup, it will go through the longest match. It will always prefer the longest match. And how? I'm going to show you. Just compare this destination with the first one. Okay, so let's start from here. 172 match with 172, 16 match with 16. Okay, that's fine. After 1, you can see there is no match. This is 0 and this is 1, so there is no match. So it will skip this one and it will move further. It will look into this destination, whether this is matching with this criteria or no. Let's see. 172 match with 172, 16 match with 16, and 1 matched with 1 as well. So if you compare these two, you can see this one is more, like the copy, or can say compatible with this one as opposed to this one. So this is gonna prefer always this one. So this will be its exit interface. So it will go there. The information will be sent throughout this. Got idea?
Yeah.
Okay. I have another example, and I want Crystal to solve this for me. So Crystal, this is the data is coming. It has multiple destinations to go through. This destination here, this destination here, this destination here. So once the data hit this router has to go through the longest match process, and it will find which is most likely, like compatible with this source. So then it will send out to the particular interface. So although the answer is there, but I want you to explain why this router choose this one.
Okay, I think
you can start from here. You can start from the first one.
Okay, so when we start with the first entry,
Okay.
in match 172 matches, 16 matches.
So,
but one doesn't match.
Exactly. Okay. So it skipped that one and then came here.
Yeah. So in the second line, 172 match, 16 match, and yes, we stop there too.
Stop there too. Why? Because
doesn't
matter. It doesn't care. Where we have zeros, it means it doesn't care, whatever it is here.
Okay.
Okay. But this subnet is different. We can see we have one here and we have two. Okay. So this is a clear cut, like can say the contradiction between these two. That is the reason it ignored this one. It came to here and it checked out that at least these two are more specific to this one. Okay.
Okay.
Because it ignored these two, the rest of it. So if this is gonna prefer S1 interface. So whenever this data will hit this one router, it will go through this longest match process and it's gonna send this information here. Then I have another one, which is gonna clear your default gateway concept. Okay, so Crystal, tell me, you can start from first, second, and then you will come to this one. Just tell me the logic.
Okay, so we start to match the first entry.
Okay.
172 match.
Okay.
17 don't match. We're gonna go to the second entry.
Okay.
172 match. 16 doesn't match.
Okay.
So we gonna take the default gateway.
Exactly. So this is the concept. If nothing matched to this destination, this is the source where the source packet is coming, but this is the destination it's heading to. It will go through this 172 match, and afterward 16, 17 there is a contradict. So it will ignore this one, it will ignore this one, and it didn't find anything. So your default gateway is intelligent enough, your router is intelligent enough, when it will hit something, get some the destination, something like which is not inside its routing table, it is always gonna send to this one default gateway. Even it is destination is 111, 222, 333, 444. If that thing doesn't exist in a routing table, it is always gonna prefer this one. Got it?
Got it.
Okay. So since we are here, I just want to explain more. Let's say we have another match here, 172.16.2.1/24. Just a minute, I will clear this one. One 172.2.0/24. Let's say this also exists somewhere here before this default gateway. So can you tell me, Crystal, now which is gonna prefer which longest prefix is gonna match with this one? Do you think it will go through this one? No problem. Just compare. That's it. Match it. Which has the longest match you are gonna prefer?
172.16.
Okay.
.00. Yeah.
Why?
Because it's matched 72.16, and you say that the 00 don't matter. So
Don't match. But what I said, the longest match. Don't forget this concept. If you go through this, just compare this one with this one. Where you reach, compare it.
So we're gonna 172 match, 16 match.
Okay.
2 match.
Okay.
And we don't care about 0.
Yeah. So don't you think this one is gonna prefer this thing is gonna prefer over this one?
Okay, I didn't understood the question. I thought that the address that you marked down was the data, and I was matching with the entry.
Okay, sorry for that if you didn't
now
get
I
me.
Understand. Yes.
Okay,
yeah.
No problem.
Longest match now, yeah.
Okay, I want to ask another question here. Sorry. Sorry, Christopher, I'm asking and hitting again and again. This is, very important concept. If you get this, the further when you will move, you will see, you will feel so much comfortable. Okay, let's suppose we have another. This is not destination. This is like in your routing information. This prefix exists. So this thing is here somewhere.
Okay.
This is what's gonna go through, or which one is going to, choose it as a destination.
The entry that you just entered, because it matched with the data exactly.
Exactly. This is the most, perfect longest match. This is one-to-one match. So this is going to, the router is going to give the priority this to over this, and even if they have 172.16, even until here, like we have here, yeah. Okay, because this is exact match, and we know the longest match is always gonna prefer. Okay. Any questions from Hefa? If you can write down, or if you have any confusion, you can ask.
I think she's good. No question
Okay.
for now.
That's fine. That's fine. Okay. If you can see in my last slide, I said find the longest match to destination. Then we have the route recursion and outgoing interface. I forgot to mention that as well. This is our destination. This is our destination. And let's say this is our source. So if this source want to reach this destination, it has go through this router. Then this router will be saying that if you want to reach this destination, you need to go into this router. Then this router will be saying if you want to reach this destination, you have to go through this router, and so on until you reach this destination. This is known as the recursion process. Recursion, route recursion. When you have to go through multiple routers to reach the destination. On other hand, outgoing interface, of course, these have some outgoing interface when this router will be thinking that if to reach this destination, I have to go through this router, but I need to go to this exit interface, this exit interface, this exit interface, and this exit interface to reach this one. So this is the concept of route recursion and outgoing interface. But sometimes what happens is when the same router has the destination, so it will come here. It doesn't need to do route recursion. We know this is on the same router, and it has only to do with exit interface or outgoing interface. So when the source will come, it is looking for the destination. It will no need to do route recursion. It will go directly to the destination, opposed to the route recursion that has to go through this whole process. I hope you have a better idea about that after that. So the longest match we have gone through. This is also very important part in the routing lookup process, that is AD. After the longest match, let's suppose we have multiple routing protocols. So this is the destination. This is destination. This is our host machine that is looking for to reach this destination. And this destination is advertised via so many ways. Like this, we have RIP domain, we have EIGRP domain, and we have OSPF domain. So it means the same destination prefix, this router is learning from multiple path as well as protocols. As I mentioned, RIP, EIGRP, OSPF. So what is going to happening on this router? For example, this computer is in question. It's looking for this destination. So which path this router is going to take when it is learning the same destination from multiple paths with multiple different routing protocols? How this router on earth is going to know which path I'm going to process first, or which path I'm going to prefer? So this is where AD comes as a tiebreaker. And if I take you to the back, the earlier slide where I was talking about the administrative distance, if you see, if it is directly connected, it has administrative is 0. What does it mean? For example, these two routers are directly connected. Okay, and this wants to communicate with this router. Since it is directly connected, so administrative distance is 0. And I told you what AD is. It is the believability. Believability means it is gonna prefer what? Of course, if it is directly connected, then it is, without, looking at other protocols, it is gonna prefer this one. Because this is directly connected. Then we have static routes, and I will discuss static routes in give you a practical scenario as well. So static route, you know, if some router is there, some host or some prefix is there, I want to reach this one, I statically will define on this router, if you want to reach this prefix, you have to, your next hop is this one. So the believability is 1. It is not directly connected, but it's connected somewhere on the router. But I am telling my this router, please, if you want to reach, I have configured static route to reach this route. So this is the believability number 1. AD is 1. Then we have a RIP. Well, I always forget RIP here. This is 120. And when we are running RIP protocol in our environment, this is where router will choose from which one I need to prefer. This is the believability. And EIGRP has this 90 and OSP have 110. And I'm gonna show in that slide, then you will have better idea. Just a minute. Yep, here. So as I said, RIP has believability 120. OSP have 110 and EIGRP has 90. When this router will check into its routing, go through the routing process and will look into its routing table. I just putting RT routing table. What do you think, Crystal? Which path is gonna prefer? RIP, EIGRP, or OSPF? I know you don't have a better understanding about the protocols, but just give me a hint or just a guess which one is gonna prefer, RIP, EIGRP, or OSPF?
I think it's EIGRP because
Why?
you say that the trust is the
Exactly.
number is
You
the
are
trust.
very good, Krista. Very good. It is gonna prefer EIGRP because this is less than this RIP and this is less than OSPF. So EIGRP is always gonna prefer. But why we are using routing protocols? This is the good point we can mention here. So let's suppose now this time EIGRP is down, but still this destination is reachable via this path and this path. Now tell me which one is going to prefer. Krista?
Yes, I'm here. Sorry, I was trying to look at the AD.
Okay, no problem.
Like you did.
AD, sorry, this is 120.
Yeah.
And OSPF 110.
Yes, he's gonna choose OSPF.
Exactly, this one. And now let's say this one is down. Then this is the last ditch effort.
Yes.
Okay, so this is where AD concept come into play. When we have multiple protocols and we are learning the same destination. Got the idea?
Yes.
Here comes metric. What in case we have the same scenario, but then we have multiple paths to reach this destination, but we are using the same protocol, which has same believability, 120, 120, 120. Now, administrative distance. Crystal, can you tell me what is going to happen?
If we are using the same protocol, we're going to use the metric.
Yes. And what is metric for the RIP?
For the RIP, is it the hop?
Hop count. So AD will be ignored. Now hop count will come into play, and you know what hop count is. Hop count, to reach this destination from this source, if it choose this path, it will have to go to how many hops? 1, 2, 3, 3 hop counts here. It will choose this one. Let's say 1, and this also has 1. So do you think it's gonna choose this one?
No.
No. So this will be excluded. Now we have a tie between these two. This is also 1 hop away. This is also 1 hop away. So what's gonna happen? Just give me your, like instinct or your guess, your sixth sense. What says?
Okay. From my understanding, if we have the same, I mean, one up, the tiebreaker will be the bandwidth. If the link are different. Okay.
No. We have decided for the metric for the RIP is hop count.
Oh, okay.
That's it. This is a deadlock. You have to use the same concept, and we know it is a tie break here. Then what will happen?
Then we can choose either one. No.
Okay, no problem. We will do. We will choose both.
Oh, okay.
Okay. So this destination will be like reachable via this as well as this, like a redundancy we have.
Okay.
Or we have multiple paths. Okay. But in case, let's add, I'm going to add here router. So what will happen?
Now it's not, it's now the second part have 2 hop.
Yep.
Yep.
Yes. So this will be excluded.
Excluded.
So the only thing left is this one. So this one is preferred. Okay. And these two will not be preferred unless until this one is down. This router is intelligent enough. That is the reason we are using, protocols. This router is intelligent enough. He has these paths in its database. It has kind of RIP database where these paths are available. When this one is down, but RIP is, it's very slow convergence protocol. It's going to take around 25 to 30 seconds, to calculate again and to reach through this destination. Because now this is 3 hop, this is 2 hop, and this one is down. So this is 3 hop. Since this has 3 hop, it is going to reject this one and it's going to prefer this one. Okay.
Okay.
Got the idea? Any
Yeah.
confusion, Hefa? Any confusion? This is very, I'm not telling you again. This is the most important topic in routing. If you get the idea, you can move along with other, concepts. Otherwise, if you stuck here, I'm very sorry. In future, if whatever you are studying, you will be facing problems.